I'm Dr. James Millen. I'm Reader in Advanced Photonics at King's College London, and I run the Levitated Nanophysics group, where we study how physics changes at the nanoscale and how we can exploit those changes. I'm also the director of King's Quantum, our institutional research centre, which is a multidisciplinary research centre with the aim of exploiting quantum technologies in the real world. And I'm also lecturer in quantum theory to the public at the Royal Institution of Great Britain. We're going to take a cutting-edge, very new emerging imaging technology called neuromorphic imaging and apply it to an equally cutting-edge sensing technology using levitated sensors to build a whole new sensing platform, which will be able to do high-speed detection of forces such as accelerations for navigation, rotations, and the detection of very, very small forces which can be used for fundamental physics. We have a state-of-the-art optics lab here at King's College London, where we will levitate charged microspheres using electrical fields, which is something which we're very familiar with doing, and then we will observe and track their motion using very, very cutting-edge neuromorphic sensors. We'll try and understand how to improve that imaging, how to write bespoke tracking algorithms. So we'll be taking data from this system and analyzing it using really cutting-edge data analysis techniques. But more importantly, because these will be used as real-world sensors, we need them to be able to read out in real time. And this will involve the development of hardware and microcontrollers so that we can get signals out of our sensor streaming in a real-time way. Quantum physics is the framework we need to describe the behavior of very, very small objects, of electrons, of atoms, up to about the size of small molecules. We cannot understand the behavior of these objects without quantum physics. It makes some very peculiar predictions. And really, in my opinion, the heart of this is how quantum physics says the world works. And so what quantum theory tells you is that everything that happens in nature is a consequence of everything that could possibly happen in that same process. So everything that happens depends on everything that could happen. And this fundamentally changes the way in which quantum systems behave compared to the large, warm, noisy systems around us in the day-to-day environment. And this is really useful for sensing in a way that's incredibly hard to explain. But perhaps a way of thinking about it is if everything that my sensor does depends on everything that the sensor could do, that sensor is kind of sampling more information around about the world around it than otherwise. And that enables you to really detect some very, very small forces. Understanding noise in sensors is very, very complicated and the bane of every sensor technician's life. Because a sensor is designed to detect disturbance from the world around it. That's what a sensor does. Something happens to the sensor, you detect it, you read that out, and you say, I've detected a force. But noise is the force from the environment that you're not interested in, which you will also detect. So what kind of force could that be? That could be just due to the fact that everything is a finite temperature. So all of your devices are jiggling around a little bit because they're at a room temperature environment. Or it could be the seismic noise from the environment. So I have my sensor running away and then a car drives by and the ground vibrates and I pick that up, but maybe that's not the force I'm trying to detect. Or it could be electronic noise. So it could be that there's noise in my sensor that comes from the electronics built onto the sensor board, which isn't really a force at all. It just looks like a force when I come to analyze my data. So these are all different kinds of noise that have to be minimized. Typically, a lot of these noise sources get into your sensor physically through physical contact, physical vibrations, and the transfer of heat or electrical noise. And so a real advantage of levitated sensors is you cut that physical tether to the environment, especially when we levitate under vacuum conditions. Then we don't even have the collisions with gas to worry about. So then we can really focus our sensors down onto only detecting the forces which we're interested in. So now we get all of the advantages of having very, very tiny sensors which are sensitive to the disturbances we want to detect, but without any of the disturbance caused by noise, which is just information that you do not want. So this really excited me as to the potential of my field with levitated nanoparticles to really build real practical sensors. So I probably should tell you that levitated sensors are incredibly complicated and delicate devices, but actually it's very, very simple to build a levitated sensor. We just use spheres of glass, actually, a few micrometers in size. They're commercially available, you can just buy them, and then we have to levitate them. So the sensor itself is just a small sphere of glass, very, very cheap, very simple. And the technology that's required to levitate these objects is also well known. So there are three ways that you can levitate an object that's useful for sensing. The first is using focused laser beams. We have a lot of experience in this. The second is using magnetic fields, which is great, very low noise, but normally requires the use of expensive cryogenics. And the third is to use electrical fields, and that's what we will use in this project. And the reason we use electrical fields is this is a very, very robust way of levitating an object. Use an electrical field to exert a force on a charged object to suspend it in vacuum. And it's very, very robust so that if you put it in the back of your car and it goes over a bump, it's not going to destroy your sensor. Optomechanics is a very precise tool for controlling the motion of very, very small objects. Our tiny sensors are levitated using electrical fields. And as I said, that makes them a very robust sensor. If that sensor gets a shock, it's going to be okay. But it may not be able to then detect a very, very small force straight away afterwards. The shock may disturb that sensor and we have to bring it back to its initial state. And we can do that using optomechanics. So by introducing a laser beam into the system, when we track the motion of our objects, we can then impose a force of our own creation to stabilize our sensor, ready to record again after a shock. Neuromorphic imaging is a new technology which tries to mimic the behavior of the brain when taking images. So a typical camera will look at the view in front of it, record that entire view, put it into its memory, and then offload that for you to analyze later. A neuromorphic device will only look at change. So it only looks at what in its view has changed. And so that requires a lot less data and information than taking the entire view, meaning that neuromorphic imaging can be much, much faster. And it's also optimized for tracking the motion of objects, because what is motion other than change? Event-based vision or event-based cameras are commercial devices which integrate neuromorphic imaging into their technology. So you can buy them and they have the neuromorphic sensors in them, and they have tracking algorithms built onto the camera so that you can point your camera at something, it detects the movement of that object, and then the camera returns to you how every object it can see has moved over time. And these devices are typically used for tracking people in crowds, for tracking objects on production lines, and for tracking cars on roads. Event-based vision is important because we need to understand the motion of our levitated sensors very well if we're going to understand the disturbance to that motion. And event-based cameras typically have tracking algorithms built onto them that can track the motion of the sensor, give us that as some information coming out of the camera, and so then we can look for disturbances. However, I would say that commercial systems are very inefficient at doing this because they're designed to be completely generic. They can track people, they can track cars, they can track birds, but we're not tracking any of those things. We're tracking a tiny levitated microparticle which is oscillating backwards and forwards in an electric field. So in this project, we can use event-based cameras to design bespoke tracking algorithms to make our sensors more precise and faster. I would say there are three main ways in which a levitated sensor is quite different to other similar technologies. The first is that these sensors are very, very small, or more precisely, low mass. And the low mass means that you can detect smaller forces. So not only through levitation do you get low noise, but you can also detect smaller forces, so you get increased sensitivity and precision. Secondly, these sensors are actually very simple. The levitated sensors are a simple experimental platform, and that means it's very easy to understand. If you detect a force, then you can analyze that data in a very straightforward way to understand the force you've detected. Accelerometers in phones require quite a lot of data processing to really understand what's gone on. And this simplicity also means that they are quite low energy consumption. So compared to state-of-the-art sensors, which often need to operate in cryogenic environments, these are room temperature sensors. I think there are two major areas of breakthrough, and the first is definitely within reach of this project, and that is levitating a sensor is all well and good, but actually levitating many sensors is better. So this is well known because if you have lots and lots of sensors, the noise which they all experience can be cancelled out. And also, if you imagine if you have a whole array of sensors, then you also have the opportunity to detect the direction which a force is coming from. Imagine a little ripple waving out across an array of 100 tiny sensors. So this is a real opportunity, and neuromorphic imaging is perfectly designed for monitoring the behavior of many sensors at once. So typically, if you were to do it with standard technology, you just have to build many sensors, chain them all together, and each sensor would have to have its own data processing and readout line. Very inefficient. It starts to get very bulky and complicated to manage. But when we levitate our sensors, they can actually all be levitated together in one place in an array. And we can use one neuromorphic imaging device, one event-based camera, to detect the motion of all of those sensors at once. And in this project, we will develop both the hardware and the software that's required to be able to detect the motion and read it out of many sensors at once, cancel out common noise so our sensors become even better, and have the opportunity of being able to tell the direction which a force comes from. The second big opportunity we have is that levitated sensors are compatible with quantum technologies. Now, this project will move us in that direction, but it's still an aspiration in our field at the moment. Because our sensors are so isolated and sensitive, we should be able to control them at the level of quantum mechanics so that we can really exploit these unusual properties to get even more sensitive. The key word there is control. To reach this quantum regime, you have to be able to control your sensor really well. So I talked to you already about optomechanics, about being able to use light to control the motion of these objects. So in this project, we are going to work in this direction by building the hardware required to read out the motion very precisely of our levitated sensors in real time, build feedback loops around that to feedback onto the motion of the sensors to control it, and actually we can suck energy out of their motion to make them very low energy sensors which start to become compatible with quantum technologies. This is a hugely exciting direction in our field, and other researchers are starting to explore building gravitational wave sensors using levitated objects or even dark matter detectors.